Hello everyone, welcome back. Okay, let's get started right away. So we're doing problem 6 from chapter 12. And what you can see here is a cross-sectional view of a wire where there is current I1 flowing through the center, and then there's another layer of current distance, it looks like 2D away from the center. So and that current, when you see the X's, that means that the current's going into the page, and when you see the dot, it means it's coming out of the page. So these currents are going in opposite directions, and they have two different values. I'm just going to label them I1 and I2 and forego the actual numerical values. And for part A, what they want is determine the magnitude and direction of the magnetic field at point A. Now, the gray matter that's shown in the diagram is just an insulating layer, so there's no current contained in that, so we don't need to worry about that. It's essentially just a place where there's no current. So we want to find the magnetic field at a point A, which is a distance d away from the center current. So let's go about doing that. So this is part A. So find B at A. Okay, very good. So what we're going to want to do is, because we're dealing with a long cylindrical piece of wire, we can use Ampere's law. Ampere's law, again, is very useful when you have situations of high symmetry, which a cylinder certainly is. So let's go ahead and think about what's going on. We're going to use Ampere's law, so let me just write that down. It's going to be the closed loop integral of B dot dl, and I'm going to define all these things in a second, is equal to mu naught I enclosed. So what does that look like for our particular situation? Okay, so let's go ahead and start with actually drawing an Amperian loop. You're going to draw your loop so that it is at the distance a away. Let's call this loop CA. Let's have this the line element DL be going counterclockwise. Let's go counterclockwise around the loop. So this is DL. And let's have the B field, in this case, be aligned with that. Now, if that we can choose the direction of the B field to be like that. If it turns out to be in the other direction, it just means that the current was, typically that's not an issue, because I1, we know exactly what the current is, and because that's a positive value going out of the page, we can choose B to certainly be in that direction. That's fine. So let's move forward. Those are going to be aligned. So the trick with these Ampere law problems is the same as we have for the Gauss's law problems. We choose that loop. One of the advantages of choosing that loop is that the B field is constant on that loop, because whatever it is, 5 Tesla, it should be that same 5 Tesla at every point in that loop, because they're all equidistant from the current. So we have that this is equal to the left-hand side. Let's draw that out. CA. This is B dot DL. They're aligned, so you have that this is BDL. That's just taking care of the dot product. Now the fact that the B field is constant on that loop means that this comes out. The B is a constant along this loop of integration, so we can take it out. CA. And then this is DL. This is a closed integral. So this is just the circumference of that loop. So this is 2 pi, and the distance there was d, so this is 2 pi d times b. And what we're left with is that 2 pi d times b is equal to mu naught times I enclosed. Now let's go look back at the picture. What is the current that's enclosed? Well, that's just I1. So here, and I1 is a parameter that we know, so we can just go ahead and say that B is mu naught I1 over 2 pi d. And that's all she wrote for that one. Now for part B, we don't want to draw the full picture, but it'll be good to have it without some clutter. You have some charge I1, and then you've got another charge I2, or I'm saying charge, but I mean current, and that's going in the opposite direction. This is I2, and we're interested in finding the magnetic field at a distance b, which is 3d away from the center, but let's just draw it like this. We know that it's outside of both of those currents. So we're going to keep moving. And we are going to use Ampere's law again. And we're going to call this CB. We're going to integrate around this larger loop that is larger than the distance from the center of I2. So this is B dl equals mu naught I enclosed So let's compute Ampere's law. And again, we're going to use the same trick where the B field can come out, and essentially this is just going to be 2 pi times the radius of this loop, which is 3 times d, times b is equal to mu naught I enclosed. So now we get to the important part. So we can combine some of these factors. You've got 6 pi d times b is equal to mu naught I enclosed. Now the trick with the I enclosed is that, and we're gonna go with a convention where again we're gonna be going around this loop like this, so that this is the dl, and we're gonna assume that the B field is in this direction. If it turns out to be negative, then it just means that we picked the wrong direction and it should go the other way. That's not that big of a deal. But the point is, the I enclosed, the way that this works is that if we say that I1 is is coming out of the page is positive, then I2 going into the page is negative. And what that means is that I enclosed, what that means is that I enclosed is going to be I1 minus I2. You just take the difference of those two things, so that you've got B is equal to mu naught I enclosed over 6 pi d. And now we just evaluate B because we know what I enclosed is. This is B is equal to mu naught I1 minus I2 over 6 pi d. Now let's go look at which one of those is bigger, because that'll tell us what direction B is in. So I1 is 1.04, I2 is 2.98. So that actually means that this is negative, which means that the B field is actually going in the opposite direction. It's going like this, like that. And at the point B that we're interested in, it's going like this. So it's pointing downward. So with this one, this is downward. For part A, which I had forgotten to answer, because the B field is actually going counterclockwise at the point A, at the point A, it's going upwards because that, actually, sorry, it's going counterclockwise like so. Because of that, it's going up. And so here, the B field is that amount. And so this is going upward. Okay, so this is a simple application of Ampere's law. Something like this could appear on the quiz for sure. The other example was a little bit more involved because of the integrations. I hope that this helps. There's more examples in the book as well. Okay,